Okay, so for number 51 in physics for scientists and engineers, we have this system created by Patrick in which he's pulling on top of a rope to bring up in a certain height in a tree. Now, if we actually label these forces going on here, we know that the weight going down here, well, actually, this is going to be in our answer right here. We know that the weight of Patrick that's going to be is 320 newtons. And that the weight of this chair is 160 newtons. We also know that the tension from pulling on top of this is going to be 250 newtons. One thing that I like to think that really helps is if we consider Timmy and this part of his arm as a separate system that's actually going to pull him up, because all we're looking at here is that upward force and not the actual body itself, because that may confuse some people. Now for A, when we draw our free body diagram, what we can do is we end up labeling these masses. So let's say this is going to be Patrick and this is going to be our chair here. And then after that, we can draw these downward forces of the weight of the chair is going to be equal to 160 newtons. And the weight of Patrick to be equal to 320 newtons. Now on top of here, you can see that there might just be one force of 250 newtons bringing him up. But the reality is, if that were true, then he'd swing himself out of order. So what it can be said is, since he's going to be pushing himself up there, there has to be a duplicate force on that side to make sure that he's not going to get flinged off if he just brings himself up to the left, because then he'd just end up going this complete other direction. So we can say that really this is actually going to be 2 times 250, which is going to be 500 newtons up. So these are so far our forces. So for B, what we're going to do is solving for the acceleration of the whole system. So that means when we sum up our forces and we say this, some of these forces are going to be equal to MA, M is really going to be the mass of the chair plus, of course, the mass of Patrick. Now, the thing is you're going on weight. We only have the weight. How are we going to be able to get the mass? Well, that's simple, because we know that the net force is going to be equal to MA. If you solve for M, that's going to be equal to the net force over the acceleration. And we know what the acceleration is because he's going up in the air. Therefore, A is going to have to be equal to 9.8 meters per second squared. Therefore, what we can say is, okay, so we look at these forces here and we're going to say 500 newtons minus 480 newtons is going to be equal to, and then what we do is we add up the net force, which is 480 newtons, right? I'll do it right here. So we say that this is going to be 480 newtons divided by 9.8 meters per second squared, and that's going to give us the total mass of the chair plus Patrick. And if we do that arithmetic right, we end up with 48.98 kilograms. So we have 48.98 kilograms times the acceleration vector. And if you rearrange that, A is going to be equal to 0.408 meters per second. So now we're going on pretty good here. As for C, the book is asking, so what is going to be the normal force that is exerted on Patrick due to this block of the chair? Well, how I like to think of it is, first off, is remember how I said I like to split this arm between Patrick so we know just the separating forces that's bringing him up. and just Patrick himself. Well, if you just split that himself, we notice, oh, there's the 250 newtons, right? We don't include this side of the 250 newtons from the tension, because what we end up saying is, oh, so if we're just going to focus on Patrick for a second, we can only say that there's only going to be 250 newtons going up, because the other 250 newtons is from this separate lever arm, which, even though technically this isn't in his body in this physics world, we're just going to ignore that for a second. So in our nice free body diagram here, we can say that, oh, okay, so this is going to be the normal force. This is going to be the 250 newtons from the tension. And of course, here's going to be our main weight, which is going to be 320 newtons. And it's asking, of course, like, what is this right here? So now, well, we know that our main acceleration of the whole system is going to be equal to 0.408, because any object in the system that we solved for the acceleration is going to have the same acceleration. It's going to be equal. So we know that A is equal to 0.408 meters per second. So now what we're going to do is just plug in for that. So now we're going to say, okay, so if we're only focusing on this tension on the top, so we have 250 newtons minus, of course, so we have minus 320 newtons plus the force normal, and that's going to be equal to, so again, we do it the same way to find the mass of this object. If you only know that's going to be equal to 320 newtons, we divide 320 newtons by 9.8 meters per second squared. And if we do the arithmetic right, that's 32.65 kilograms. So 32.65 kilograms times 0.408 meters per second squared is going to be equal to 250 newtons minus 320 newtons plus Fn. So what we're going to do is we end up solving for this, and we rearrange this to say f of n, that's going to be equal, and then we multiply this out, 32.65 times 0.408. That's going to be equal to about 13.3212. Then plus 320 newtons minus 250 newtons. And once we solve for that, the force normal in newtons is going to be, again, if we manage to do this through it, it's going to be 83.32 newtons. And that is our answer.